Welcome back. So now we want to find out what is the distribution of the received signal R given the constellation point SI. So suppose you have this received vector R which has these projections R1 all the way to Rn onto the basis function phi j of t. Remember your system model is that you have transmitted the signal Si of t in a Gaussian channel where a white Gaussian noise gets added on top of your signal Si of t, and you get this received signal R of t, which is nothing but Si of t plus n of t. So if n of t is a Gaussian process, given Si of t, your R of t would also be a Gaussian process. And this vector R would be a Gaussian vector. So this would be a Gaussian vector. So it's a multi-dimensional vector, n-dimensional vector, and you need to compute what is the PDF or the distribution of this Gaussian vector R given a constellation point Si. So in order to compute that, let's compute a couple of things first. Let's start with the expected value of Rj given Si. So expected value of Rj, where j can vary from 1 to capital N, given a constellation point Si would be equals to the expected value of, remember Rj is nothing but Sij plus Nj given Si, and if you are given Si, you also know what is Sij, so you can equally write that given Sij. And now given Sij, this mean of this function, because mean of the noise is 0, so the mean of this function would be nothing but Sij. So expected value of Rj given Si would be nothing but Sij. You can call it mu Rj given Si. Similarly, you can compute what is called the variance sigma square of Rj given Si, which would be expected value of Rj minus this mu Rj given Si whole squared, and that would be equals to expected value of Sij plus Nj minus the mean, which is nothing but Sij given Sij whole squared, and then you can see that this would be nothing but expected value of Nj squared, and that would be equals to N naught by 2. So we are assuming that the variance of the noise is nothing but N naught by 2. So N naught by 2 is uh, representing your variance, noise variance. So you can also prove, and it has been proven in the textbook, so we are not proving in it in detail, but our goal is to find out what is the distribution of the received signal R given Si. So you can find out what is called the covariance of Rj Rk given Si, and because of the orthonormal nature of the basis function, if you expand this Rj and Rk, because these Rj and Rk is nothing but the projection of R of t onto the basis function phi j and phi k respectively, you can very easily prove that this covariance would be equals to 0 if j is not equals to k, and this would turn out to be equals to n naught by 2 if j is equals to k. And because that we have already proved that if j is equals to k, this covariance would be nothing but the variance of the noise, which we are assuming to be equals to n naught by 2. But the important thing is that these two vectors the rj and rk are independent, they are uncorrelated, to each other, and because these are Gaussian random variables, these are independent as well. So now because these components Rj and Rk are independent to each other, we can write down the joint distribution of the vector R given the constellation point Si, because the joint distribution would be nothing but the product of the individual marginal distributions. So we can find out what we can write out what is the PDF of the received vector R given the constellation point Si, and that would be equals to a Gaussian distribution, product of the Gaussian distribution. That would be equals to 1 over root 2 pi sigma squared, where sigma squared is n naught by 2, n naught by 2 cancels this 2, raised to the power n by 2, e to the power minus 1 over sigma squared, 2 sigma squared, that would be 1 over n naught, times Rj minus the mean whole squared. And of course, because you're taking the product of all these, there would be a summation sign here, and the summation would be j equals 1 to capital N. So this would be the PDF of the received signal vector R given a constellation point Si. So this is an important distribution, because this distribution would be used in the maximum likelihood detection criteria as well. So let's try to discuss what is the maximum likelihood detection criteria. So the maximum likelihood detection would would try to minimize the probability of the error of a given of from the received signal. So the goal would be to find out what was transmitted given the received signal R. So once you have the received signal R, so the goal of the receiver structure is to find out what is what signal would have been transmitted, and the maximum likelihood receiver would try to find out the what is the most likely symbol that would have been transmitted. So what symbol, for which symbols the likelihood of transmission is maximum, right? So maximum, uh, as I've said, so the maximum likelihood detection would try to find out which constellation point was to be transmitted given the received signal R. So you have this received signal R. What is the most likely signal that would have been transmitted? And what it does is it tries to minimize the probability of error, or in other words, it tries to maximize the probability of correct detection by minus PE, which is nothing but the probability of correct detection. So the probability of the correct detection 1 minus PE would be equals to what is the probability of M hat sent given the receive vector R, and the optimal receiver tries to do what? it tries to compute the to find out an I such that the probability of Si sent given the receive vector R is greater than or equals to the probability of Sj sent given the receive vector R for all j equals to 1, all j not equals to I, and j can have the values from 1 to capital M. So for all constellation points, let's try to find out which is the probability, what constellation points has the maximum probability of the correct detection, that is the probability of Si sent given R, for which constellation point from I equals to 1 to capital M this probability is maximum. So that is the goal of the maximum likelihood receiver. Now we can use some of the basics of the probability to make it to compute what is probability of Si sent given the receive vector R. Using the Bayes rule, we can see that this would be equal to the probability of R given Si sent times the probability of Si sent divided by probability of R. So that is an important rule that we have used. But the important thing is that this probability of Si sent would be a constant. So for example, you would have all the constellation points to be equally likely to be sent. So that is the a priori probability, then that is known already. This probability of the receive vector is independent of Si. So what you're left with is probability of R given Si. And if you want to maximize this left hand side, you need to maximize probability of R given Si. And probability of R given Si we have just computed, which is a boxed relation. You can see on the screen as well. So this relation P of R given Si, you would try to maximize this this distribution, and the SI which maximizes this distribution given the receive segment R would give you what? Would give you the most likely symbol that would have been transmitted. So let's go ahead and compute that. So now what we know is that maximizing probability of Si given the receive vector R is equals to maximizing the P of R given Si. Now P of R given Si, remember, is a jointly Gaussian distribution which for independent random variables, and that was a product of capital N number of capital N number of Gaussian distributions. So maximizing this is that would mean that you want to maximize that Gaussian distribution. Also, because of the concave nature of the log, maximizing something, so we can also call this to be a likelihood function. So maximizing P of R given Si is equivalent to maximizing natural log of P of R given Si. And this natural log of probability P of R given Si is what is called the log likelihood function. Call it L of Si. is nothing but the natural log of P of R vector given Si. Recall what is your PDF. PDF you want to maximize is given here, right? So you have this jointly Gaussian distributions, right? So the mean of these distribution is Sij, right? Rj minus Sij, mean is Sij, and this is a jointly Gaussian distribution. So if you take the natural log of this, so you can clearly see after taking the natural log, you would be left with this thing that you want to maximize. And you can see that you have a negative sign here. So maximizing this would be equals to minimizing this function without a minus sign. So let's go ahead and write that down. So what we want to do is to maximize over the constellation point Si, because that we want to compute minus 1 over n naught summation j equals 1 to capital N Rj minus Sij whole squared, and this is a negative sign. So you can equivalently write this as minimizing over Si, and this 1 over n naught is a constant. Um, you can just take care of it, and what we write is summation j equals 1 to capital N Rj minus Sij whole squared, and this because both R and can be written in the vector form. Essentially what you're doing is you would be maximizing over the constellation point Si R minus Si mod squared, because if you want to compute the distance, Euclidean distance between a vector R and the vector Si, all you need to do is to take the difference of all the elements, take the square and sum from for all values j equals 1 to capital N. This is nothing but sorry, this is minimizing. So this is nothing but you want to minimize the distance between the received signal R and the given and the constellation point Si, and the constellation points I that minimizes the distance between the received vector R uh, with the constellation point Si would be your decision. So if you want to visualize this, for example, let's take an example of QPSK. So suppose you have these constellation points, and suppose you have this receive signal R, right, as a vector. Remember both of them, both the constellation points and the receive vector can be represented as a linear combination of the projections onto the basis function. So you have these four constellation points. Remember, this would be phi 1 of t, this would be phi 2 of t. So once you have this received signal R, you would compute the distance of the received signal R from all the constellation points, and the constellation points with which the distance is minimum, right? You would say that that constellation point is the most likely that would have been transmitted. So what you do is you make decision regions. So the rule for the decision regions would be, so what are the regions in which the distance from this constellation point is minimum, and the region I have drawn is the region in which the distance from S1 is the minimum. This shaded region is the region where if you receive a receive signal in this region, then you would decide in favor of S1 because the distance from the S1 is minimum in this entire region. Similarly, you can make this region, I can shade it with this, would be the region where the distance with S2 constellation point would be minimum. Similarly, this region shaded in black would be the region where the distance where S3 constellation point would be minimum. And finally, you would have this region where the distance with S4 would be the minimum. Right? So in this region, let me right. So in this region, in this black shaded region, you would have the distance with the S3 constellation point would be minimum. In this black shaded region, the distance with the S3 shaded point would be the minimum. In this entire region, the distance with S4 would be minimum. Right? So these are the decision regions, and the rule is called minimum distance rule, which makes intuitive sense as well. So the maximum likelihood decision criteria at the end would do what? Would compute the distance of the received signal with all the constellation points, and the constellation point with which the distance is minimum would be would be the one which would be detected. In other words, if you want to write this stuff mathematically, so you would decide in favor of Zi. So we'll decide in favor of Zi, where Zi would be equals to R such that R minus Si mod is less than R minus Sj mod for all j equals 1 to m and j not equals to I. So that would be the rule written in the mathematical form. In the graphical form, this is nothing but you would come for a given received signal R, you would compute the distance with S1, S2, S3, and S4, and the distance and the region and the constellation point with whom the distance is minimum, you would decide in favor of that. And for that, you can decide already. You can draw decision regions. So once you have the received signal, all you have to do is find out in which decision regions your received signal is falling into. So if it is falling into the decision region for S1, you decide in favor of S1, right? And that would be the most likely symbol that would have been transmitted. There would still be the error probability. So if the noise is such that it pushes your received signal beyond this region into the region S2, and when S1 was transmitted, then of course you would make an error. Similarly, if the noise is such that it pushes your received signal R beyond this into the region of S4, you would again make an error, right? But this R would be the most likely symbol. Symbol that would have been S1 would be the most likely symbol that would have been transmitted.